Let me give you a nice example of a very easy problem that can't be solved by a computation. It's a theorem that goes back to Euclid, so 2,000 years old. It turns out that there's infinitely many prime numbers. This is a consequence of the Goldbach conjecture. If there were only finitely many prime numbers, like if there were no prime numbers bigger than 1 million, then if you had an even number bigger than 2 million, then there aren't any prime numbers big enough to add up to it. So one consequence of the Goldbach conjecture, which we don't know, is the fact that there must be infinitely many prime numbers, but it turns out that this was a theorem of Euclid. This was in Euclid's Elements. So how are we going to prove that? Well, hopefully I've drummed it into you that we can't prove that by doing a computation, right? We can't write Python code that will prove there's infinitely many prime numbers. What we can do, though, is we can write Python code that will just print out prime numbers, right? We can just like work out some test. A number is prime if it doesn't have any factors which are less than it. If the only way to break it up, you can't break it up into a product of two smaller factors. So it's easy to write some Python code that will just print out lots of prime numbers, and then you go and have some tea, and you come back and it's still printing them out, and then you kind of go to bed, and you get up the next day, and your computer's quite hot, but it's still printing them out. And so this is evidence that there's infinitely many prime numbers, but of course it's not a proof that there's infinitely many prime numbers. So this is the problem with using computers in a traditional way, using computers to compute. But nowadays, we can use computers to prove there's infinitely many prime numbers, right? This is the new thing. This is the new thing. And in fact, I'm going to use computers in 2 different ways to prove that there's infinitely many prime numbers. So there you go, 2 for the price of 1. So 2 ways to do this. And the first way is we're going to use a large language model. So ChatGPT, that's a thing. Maybe some of you have heard of it. It's been in the news like all the time for months and all over Twitter. And we can ask ChatGPT. And if I was more risky, I would now switch over to a tab and we could do it in real time. And I tried this. I gave a warm-up for this talk last week, and I switched over to the ChatGPT website. And it was a Zoom talk, and I had an audience of people, and ChatGPT was like, nah, busy. Great. So sitting there, failing to use ChatGPT. So this time I got it. I did it before. So I did a screenshot. So there we go. I asked, what did I ask? I said, can you give me a proof that there's infinitely many prime numbers? And the answer is yes. And not only that, it's going to give Euclid's proof. And there it is. And you read it and it looks good. This is Euclid's proof. You don't have to read it. Maybe you know Euclid's proof already. There's a trick, right? What you do, if you've got, you can't see this slide. I'm really sorry. I'll just tell you what it says. It says, say we've got finitely many prime numbers, P1 up to Pn. We've got finitely many, and then what we're going to do, here's the trick. We want to make, what does it mean to have infinitely many? It means if you've got a bunch of them, then you can make another one. If you've got finitely many of them, then that's not all of them. So we've got finitely many, P1 up to Pn, and now we need to make a new one. And so what you do is you multiply them all together, and then you add 1. That's the trick. So that's the brilliant idea that's in Euclid's Elements. And you multiply them all together and you add 1. And now there's 2 possibilities. And the first possibility, that number's clearly bigger than all the numbers we started with, right? Because we start off with a bunch of numbers and we multiply them all together and now we've got a much bigger number. And then we add 1, so it's even bigger. And if that number's prime, then we've won. And if it's not prime, then that's okay. Because if it's not prime, then it's got some prime factors. And it's not difficult to check that one of those prime factors, that if you've got a prime number that divides n, and it's one of these numbers we know already, then it's going to divide n minus 1 as well. And if you've got a prime number that divides n and it divides m, the set of numbers that a prime number divides, they come in little, the equally spaced blocks. There's the multiples of 7, there's difference of 7 between them, right? So you can't have a prime number that divides n and n minus 1. And so a prime factor of n can't possibly be one of the primes we have. So there's Euclid's proof. And the large language model has a go at explaining that. And you read it and it's kind of sort of right, but it's actually not that, it's you can't see it, so it's not that good. It's a 7 out of 10 proof, right? That's what it gives you. And that's not bad. That was one shot. That was the first time I typed this thing into ChatGPT and I took the screenshot. And I give it 7 out of 10. Because if it's prime, the logic is fine. If it's composite, it just wrote stuff that didn't quite make sense, but it clearly knew that it was on the right lines. And I imagine that if you just asked ChatGPT the same question several times, eventually you would get a 10 out of 10 proof. And so you get the impression that actually getting ChatGPT to prove there's infinitely many primes is just like asking a room full of 300 undergraduates, just like, write down a proof there's infinitely many primes, and then they hand something in, and you'll get good ones and bad ones. They'll all kind of know it, but some of them will also explain it well, and some of them will explain it poorly. And that's not surprising because ChatGPT is trained on the internet, and a lot of the internet is written by undergraduates. So it's copying what it sees, right? So there's infinitely many primes. That's great. So here's a harder problem. I claim there's infinitely many primes that end in 7. So there's the first few. 7 is a prime. 17, 37, 67, and 97. Those are all primes. And again, you could do the same thing. You get Python to start printing stuff out. You could get Python to start printing stuff out, and you can note that it doesn't seem to be stopping. But it turns out that actually this is much harder. This was not known to Euclid. This is a genuinely deeper result. It was only proved about just over 100 years ago, about 130 years ago. This was proved, and it's genuinely deeper. And the method we have doesn't work. Okay, so let's ask ChatGPT, can you prove that there's infinitely many primes that end in 7? And it says yes, and it just writes out the same thing, right? It slightly modifies Euclid's proof. And this is a really good idea. So it says, let's say there's only finitely many, P1 up to Pn, and then we make a new number, which is product them all together, multiply by 10 and add 7. And that's a really good idea. If you're an undergraduate, and you know the proof there's infinitely many primes, this is a really good potential looking start, right? Because we've got finitely many primes, we multiply them all together, that will give us a random number, and then we multiply it by 10, that's a big number that ends in 0, then we add 7. And this looks good. If that number's prime, then we've won, okay? And if it's not prime, then we get stuck. That's what actually happens. But the language model doesn't get stuck. It just sort of copies the proof that there's infinitely many primes, right? Because it's seen the proof that this technique does work in more. You can prove there's infinitely many primes that have remainder 3 when you divide by 4 using the same method. And probably it's seen proofs of that on the internet. So this technique that it knows, it does generalize a little bit, but it doesn't go as far as proving there's infinitely many primes that end in 7. So this is a great start, but it's actually, I know it doesn't work, but I know that this is hard. And this bit's rubbish, it turns out. And then it's just like, in either case, we found a prime number that works, right? So there we go. So this gets 0 out of 10, but unfortunately, it does exactly, again, if you gave a bunch of undergraduates the same question, that is exactly what they would do, right? Because they know this trick. They don't know it's hard. They know this trick, and they figure, let's try and generalize the trick, right? So it's a very sensible approach, but it turns out it doesn't work, and the language model just doesn't spot that it doesn't work. Because it knows that this kind of thing sometimes works, and it's seen examples on the internet where it does work, and so it has a go. It will work to prove that if you write numbers in base 4, it can prove there's infinitely many primes that end in 3. And the reason is if you've got a large number, which is 3 mod 4, and it's a product of prime numbers, one of those prime numbers must also be 3 mod 4. But that doesn't work here. This is the problem. You can have a number like 57. That's a large number that ends in 7. 57 is not prime. It's 3 times 19. And this is the problem. You've got a large number that ends in 7, but it's a product of 2 smaller numbers, but neither of the smaller numbers ends in 7. And that's exactly why the method doesn't work, and that's exactly why the question is hard. And the large language model has no idea, because it's not thinking, it's just sort of seeing that this technique sometimes works, and it's just confidently saying, yeah, it works in this situation. The system doesn't notice, it gives a plausible but utterly wrong answer. So, okay, last language model, right? It's just trying to get the marks, right? That's the thing. It knows a technique that sort of works, and so it tries to generalize it, right? It knows a method, and it can't think of anything else, so it tries the method. So I asked ChatGPT to prove that there were infinitely many even numbers that end in 7, right? That is not actually true, it turns out. Okay, but I asked it, can you prove there's infinitely many numbers? And it does just the same thing. It's exactly the same trick. Like, so here, this proof isn't right either, it turns out. And in fact, there's some dubious, I mean, yeah. It even says, this is a contradiction, since even numbers cannot end in 7. It even mentions the fact that there's no even number that ends in 7. But it knows a method, and so it tries the method, right? So now the question is, are these large language models going to take my job? Right? And for me, the answer is no, right? Not yet. Because I can't see it. I can see that ChatGPT is a spectacular thing, right? It can write a washing machine manual in the style of Shakespeare. I mean, it can do all sorts of things, but it can't do mathematics beyond some point. It can't do second-year undergraduate level mathematics, right? They have got, I can see why the computer scientists are excited, because they are right, they're doing the dumbest thing, right? They're just predicting the next token in a string of tokens, and they are writing grammatically correct English. Right? They're doing astounding things. They couldn't do that 5 years ago. They're writing grammatically correct English. They're clearly getting exponentially better. Okay, and they've got really good at doing a bunch of things which aren't the kind of questions that I was just talking about then. Okay, I'm not denying that. They're absolutely great. But the thing is, the question is, will this exponential increase continue? And will it, in 5 years' time, will I just be sitting here, will I be feeling like an idiot and it will be doing research level maths? And I just can't understand, right? There are people on Twitter that just tell me that I'm going to be out of a job in 5 years' time. And I don't believe them, right? And of course, time will tell, right? But I can't see. I mean, already they trained on the entire internet, right? I don't see, what are you going to train on next? I just don't see where this is going. So I might be wrong, right? I might be wrong, but at the minute, I'm not scared of ChatGPT. So let me tell you something else I'm also not scared of. I'm going to give you another proof that there's infinitely many prime numbers. And I'm going to do it using an interactive theorem prover, which is a completely different kind of thing. So let me switch over to my interactive theorem prover. Here we go. And my example, so this is a system which knows the axioms of mathematics, but it doesn't know any mathematics. It has no idea what a prime number is. But it's okay, because we're building a maths library, and in the maths library, we write down the definition of a prime number, and we put it in a file called data.nat.prime. And we prove some basic theorems about prime numbers in that file. So let's import the definition of a prime number, and now let's say, now we've got to figure out how to state that there's infinitely many primes, so I'll do for all naturals n, that's upside down A is mathematician speak for all. For all upside down, for all natural numbers n, there exists a p such that n is at least p. So what I want to say is, this is just the easiest way to explain that so if you give me a number, I can find a prime number that's bigger, right? That's the same thing as saying there's infinitely many. For all natural numbers n, there exists a p such that n is at least p and p is prime. Nat.prime p. There we go. So there's the statement. And an interactive theorem prover turns this into a computer game, right? And undergraduates really like computer games, and I use this in my courses, and I run a club where I teach my undergraduates. And there's a bunch of, there's a thing going on in London with undergraduates at Imperial, and there's a bunch of people that could now start, you can type in, you're in puzzle game mode now, right? There's the goal. So let's let n be arbitrary, intro n, and now I've got to prove, so now n is a natural number, and I've got to prove there's a prime number. There we go. So this would be let's use 2 times n plus 1. This isn't going to work, right? But what I'm saying, I'm claiming that 2 times n plus 1 is going to work. So now I've got to prove that n is less than or equal to 2 times n plus. I can do that, right? So now I can do split. Now I've got to prove that n is at least 2 times n plus 1. That's true. But I've also got to prove that 2 times n plus 1 is prime, and that's not going to be true in general, right? If n is 10, then 2 times n plus 1 is 21. So this proof this is like an undergraduate that's taken a wrong turn. But we can just do Euclid's proof. I can type in Euclid's proof, but I'm not going to type in Euclid's proof. I'm going to do library search. So that's a tactic that just looks through the library, and it's got very exciting. It's given me some output here. It's done it, by the way. It says goals accomplished. It's got very excited because it's proved it. So we could click here, and this is the proof it's discovered. So it's proved there's infinitely many primes. So there you go. So the computer has somehow generated a proof that there's infinitely many primes, right? So you should be like, is there something a bit fishy going on here? But I've asked it to prove a theorem, and it's telling me it's proved the theorem. That's true for sure. It's telling me it's proved the theorem. So what exactly just happened? So Lena's proved it automatically. It somehow found a proof that there's infinitely many primes. And did it actually find it by cunningly writing some weird computer code that corresponds to it? Like, what actually happened? It turns out what actually happened is that we've got a gigantic mathematics library that we've spent the last 6 years writing, and it's got 110,000 theorems in, and one of those theorems turns out to be a proof that there's infinitely many primes. So where did those theorems come from? Those theorems were all typed in manually by humans, several of which were the undergraduates I'm teaching at my university, and several of which are other people, located at random universities around the world. And we're all collaborating together, making a gigantic open source mathematics library. And so let's actually have a look at what actually happened there. So we could right click on this, and we can go to the definition. So here we are. So we're in data.nat.prime. That was the file I imported. And lo and behold, on line 418, here we have some kind of computer code. And this is computer code written in a functional programming language. So that's, for the computer scientists, this is functional. This is all syntactic sugar for some big function. But somehow a proof is the same thing as a function. It's quite surprising. Here's the key idea. There's n factorial plus 1. We don't do the product of the primes less than n. We do the product of all the numbers less than n, and then we add 1, and then min fac, if we hover over that. There we go. It returns the smallest prime factor of a natural number. So we let p be the smallest prime factor, smallest prime factor of n factorial plus 1, and then we prove some facts about it. There we go. We prove that p is prime, and we prove that p is at least n, and the proof is by contradiction. If p isn't at least n, then p is less than n, and so if p is less than n, then it's one of the numbers less than n, and n factorial is the product of the numbers less than n, so p will divide n factorial, but p definitely divides n factorial plus 1, because it's the smallest prime factor of n factorial plus 1. So it divides two numbers which are next to each other, and so it divides their difference, which is 1, and then we get a contradiction, and there we go. So that proof was typed in by a human, right? It's just Euclid's proof again, but typed in by a human. So the computer didn't magically prove it, right? But a human proved it, and then the computer noted that a computer found it, but a human put it there. So Lin can also prove there's infinitely many primes that end in 7. And I told you that was much harder, okay? So this is the thing about interactive theorem provers versus large language models, is that interactive theorem provers can get further. So it can prove there's infinitely many primes that end in 7. And the proof isn't in its mathematics library, and those of you that know something about software libraries will realize, the moment I show you what the proof looks like, let me show, this is what the proof looks. This is part of the proof. And this is just gobbledygook, right? This is there's V3 and V4 and V, all the variables are called V, and we've got no idea what any of them mean, right? And so where did this monstrosity come from? That turns out it's like hundreds of thousands of lines long. But no, it's over 100,000 lines long, and it all looks like this, and there's no comments and there's no explanation. And the reason it looks like that is because that proof actually was written by a computer, which is kind of amazing, right? Because I told you that theorem was really hard, but I'm still lying. That proof was, I'm not lying yet, that proof was written by a computer, and as I say, I can't read it, But I can compile it, right? I can type it, I can copy and paste it into Lean. I can run Lean on those files, and Lean runs through and says, yes, this is an error-free proof that there are infinitely many primes that end in 7. So that's kind of great, but I'm lying, right? There's some lie, there's some secret. So here's the secret. That proof that was written by a computer, it turned out that the computer was translating another proof. And the other proof was written in another interactive. There's loads of these interactive theorem proofs. There's like 20 of them. And they're all used by different communities to do different things. Some of them are used to check that code has no bugs. They're used to verify hardware and software and compilers and kernels, lots of computer science things. Some of them are used to do mathematics. MetaMath is another one. It's used to do mathematics. And the MetaMath library, it's got a handwritten proof, right? So in another theorem prover, somebody, a human called Mario, typed in a proof that there's infinitely many primes. And then he wrote a program that will translate MetaMath proofs into Lean proofs. And then he ran his program on his proof, and he got 150,000 lines of garbage, of incomprehensible but correct mathematics. So this is disappointing, because I still haven't shown you computers doing mathematics, right? So how far can interactive theorem provers go, right? That's an interesting question. How far can we actually push these things? So we've seen them get to the year 1900. And the big news really in the area over the last few years is that actually we can get them to now. And that was something that all the computer scientists kind of knew, but somehow the computer scientists don't really know what's happening at the forefront of modern research mathematics. So the computer scientists weren't doing it. And in some sense, one of the things that in some sense I'm proudest of recently is I've managed to get the mathematical community to notice that these things exist. And the moment mathematicians got their hands on them, things have been really happening. So it turns out we can get to modern mathematics. So this is Siddhartha who introduced me. This is his blog. So he formalized, this is a great example. So I'll read you what it says, because it says a little over a year ago, Giles Gardner disproved a long-standing conjecture, often called the Kaplansky unit conjecture. Blah, 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 blah. And then Anand Rao Tidipatri, who's also in the room, and they formalized Gardner's disproof in Lean. So what they did was they took this paper that came out in 2021, and they taught it to the computer, that and all the prerequisites needed, and they taught it to the computer. So the computer knew, in 2022, the computer knew a result that was proved in 2021. This was something I did completely as a gimmick. This was something that really made the mathematics. Peter Scholz, who got a Fields Medal for defining perfectoid spaces and proving some theorems about them. And I looked at the definition and thought, well, we could easily teach this to Lean. And we taught it to Lean, and there was sort of excitement on Twitter and on, there was some sort of excitement in the maths. This was the result. This was one of the results. This was something that contributed to mathematicians waking up and noticing that these things were coming. So we formalized perfectoid spaces, and we got a publication out of it. And then we started on a very deep theorem of Peter Scholz that was proved in 2019, Scholz and Clausen. And when we were halfway through, Nature got in touch. It was like, what the heck are you guys doing? And it was wonderful to see pure mathematics in Nature. We'd somehow got halfway through proving a spectacular new theorem of Scholz when we got a big write-up in Nature. So this was sort of amazing. And so there we go. So what have we seen so far in this talk? I've just finished the main section here. I'm going to get on to the last section. What have we seen so far? We've seen that a large language model can write maths by itself. But the large language models, beyond some point, you have to, it's hard to stop trusting them because they're sort of confidently spouting rubbish. On the other hand, interactive theorem provers don't make mistakes, unless there's bugs in the kernel. Which hopefully there aren't. So they don't make mistakes. I mean, they are orders of magnitude more accurate than humans, that's for absolute sure. They don't make mistakes, and we can get them to the boundary of modern mathematics, so we can get them to the point where they're threatening my job as a researcher, but unfortunately, they're not doing it by themselves. The only way they can get to the boundary is we hold their hands. Right? We take the maths proof and the literature and we translate it. So that's not going to be removing my job either. But, so both of these things have got a big weakness, right? The large language model talks nonsense. The interactive theorem prover, we need humans to type it in. So we need to put them together, right? Because the weakness of each system is the strength of the other one. This is the key thing. So we've got to put them together. And people already had that idea, right? But only a few years ago. Let's put them together and, I don't know, let's get the large language model to write lean code. Because then the large language model can't write rubbish. So there you go. And it's happened. This is quite rubbish. This is a rubbish proof of a relatively simple question. This is a proof of the fact that if you take any natural number n and you look at 2 to the n plus 1, that's some large natural number. And the claim is it's never a multiple of 7, it turns out. And the proof, it turns out, it's quite easy to do by induction if you know what you're doing. So this was half of a question on an old International Maths Olympiad. 1960, but like really old. The International Maths Olympiads were much easier in the old days, in the very old days. So this is a kind of a question that you would never see on a modern International Maths Olympiad. This would be bread and butter now for people training to do International Maths Olympiad. But at the end of the day, it was half of an old International Maths Olympiad problem, and Facebook took one of their large language models that was trained to write computer code, and they trained it to write lean code, and then they left it, and lo and behold, it actually cracked it. And the proof is lousy. When you work out, like you look at it, the proof is lousy. I would give this 3 out of 10 for style, because they apply induction on line 6. You prove it by induction, but you don't do it like this. You prove induction on line 6, induction again on line 7. This is kind of induction. That's kind of induction as well. And then, for good measure, once more, induction again on line 6. So when you actually work out what it's doing, you can translate that back into human language, and you can see it's just making a meal of it, really. So for style, I give it 3 out of 10. But for mathematical accuracy, I give it 10 out of 10, because it is a completely rigorous and correct proof of an International Maths Olympiad question. You can't, and the reason we know it's a correct proof is it compiles, right? The computer says yes. So it works, and so that's a proof. So that's kind of amazing that we are at the stage where large language models can write code, which is, in contrast to the infinitely many even numbers that end in 7. This is code that's guaranteed to be correct, written by a large language model. So that's great. So that's the first time in this talk that we've actually seen computers doing something that's arguably amazing, right? But, okay, it's actually like it's school level, right? It's first year undergraduate level, and that's state of the art. So in some sense, we've still got nowhere, because we've already seen that the large language model by itself can do that kind of level mathematics. Okay? But there is potential here. I think there's more potential. So maybe in 5 years' time, maybe we will be seeing some growth here. But I kind of like that idea. So far, I'm not scared of being replaced by a computer, because I've already got a system that can do mathematics at undergraduate level, and it's all the undergraduates, right? Free and easy access to hundreds of gadgets that will do mathematics at undergraduate level. And if I want them to do something, I just, I put it on the homework. So maybe right now, okay, undergraduate level, fine. Research level looks impossible. So maybe we need to, sometimes, you can't just say, okay, now do research level, right? You have to find the right question. So we need to find an easier question, so I'm going to spend the last 15 minutes talking about an easier question. And so what do these things do? Something else I do is teach. I don't just do research, unfortunately. I did just apply for a huge grant from the British Pure Maths Grant Funding Agency to get me off teaching for 5 years so I could prove Fermat's last theorem in lean. That would be kind of good if that comes off. And if that happens, then my job won't be teaching. I'll have 5 years to do some completely bonkers, like crazy blue sky nonsense. But let me talk about teaching, because I still do it right now. So what does teaching look like? Well, undergraduate teaching, we kind of know what it looks like, right? I give undergraduate lectures, and then at the end of the lecture, students come along and ask me questions, and some of them ask me really stupid questions that just proves they weren't listening, and some of them ask me really intelligent questions that proves that they were not only listening, but they were thinking. And that's what teaching looks like, as I'm sure everybody knows. And during COVID, I couldn't go in and give my lectures in person, and so I gave them all on Microsoft Teams, and they all got recorded by my institution, so my university's got them, right? So I'm halfway to being replaced. I'm halfway to being replaced by computers already, right? So, you know, even the jokes, they record the jokes as well. So what's left? What's left is the one-on-one conversations, right? So, and now you kind of think, well, maybe actually a large language model might be able to do this, right? So right now, I would say maybe no, maybe yes, but I'm not convinced they're going to get exponentially better and they're going to be proving the Riemann hypothesis or the Goldbach conjecture, but I don't know, maybe they're going to be maybe they're going to be having those one-on-one conversations. I'm not confidently predicting that that's never going to happen, right? And but at the minute, I can see it happening for my basic introduction to proofs course, but I can't really see it happening for some kind of final year undergraduate course. You know, my experiments with large language models is just, you know, at some point they just, you know, they extrapolate in ways that it just, you know, that's the problem, right? They extrapolate to give incorrect things because they don't really understand, but they're very good at pattern, you know. Oh, this technique proved this. They've changed the question a bit, so I'll just change the answer a bit. Right? That's what they're doing. So, okay, so I can see that happening. So we need a good challenge problem that isn't utterly ridiculously impossible, but is maybe, you know, so what about supervising PhD students, right? That's sort of next level up from undergraduates. Can they supervise my PhD students? So what does it look like in pure mathematics? So here, you all know what it's like to teach because you've been taught and many of you do teach. But supervising PhD students, I think this is kind of subject specific. So let me tell you the way that I typically start off with a PhD student, right? If I've got a PhD student doing a PhD in algebraic number theory, what does this look like? And often the thing to do, I get them to warm them up. I'll give them a problem which the experts or the snobs or whatever you want to call them would call incremental. Right? This is if you ever want to reject, if you're sending something to referee from a top pure maths journal, and you want to kill it, you write a jolly nice report and you say somewhere that the result is incremental, which just means that like any expert could have done it if they could have been bothered. It means that the techniques are just about there, and it's just that nobody wrote them down yet. And so let me give you an example of this is what an incremental result looks like. 20 years ago, there was an excitement about foo theory. So foo is a mathematical thing, right? So there's a foo theory, and there was a great paper in foo theory called Paper X, and it proved a famous theorem about foos. You know, the main theorem of foo theory, the fundamental theorem of foo theory. But since then, there's been developments, and now there's this kind of generalized foos, which are different objects. And, but generalized foos behave like foos in many respects. And the thing is, this theorem about foos, it should probably generalize to generalized foos. But the thing is, the result isn't in the literature. Because this paper X was proved about foos when foos were state of the art and generalized foos came later. And so now the question is, we want to rewrite paper X because it's not proved in the right generality for 2023. So you give the paper to the student, you say, can you check that this paper works in generalized foo theory, right? So, and as I say, that's not because I think this is going to be a fabulous breakthrough result, right? This is an incremental result. But on the other hand, you might be able to get a publication in a weak journal, and that gives the student some confidence that they're doing something right. And it also gives me, I want this because I want to prove a brilliant theorem about generalized foos. But one of the obstructions is that I don't have the analogous result. So ultimately, when the student's faced with this is the kind of question they have. The foo theory paper just goes on and on and on. The argument is quite long. And at some points it says, well, obviously this fact is well known to be true for foos, right? And now the student's trying to cross out the word foo everywhere in the paper and replace it with generalized foo. That's what the student needs to do. And so the student needs to figure out, you see, the student's being forced to read the paper. This is why this is a good project for a beginning PhD student. They're learning the area. The student needs to figure out whether this analogous claim is also true for generalized foos. And the problem is, the paper is just saying, oh, this is a well-known fact about foos, right? And the student barely knows what a foo is, right? Because they've just started. So they have no idea whether this claim is true. They probably don't know why it's true for foos, right? They might not know. And even if they do know, they might not really understand the proof well enough to be able to push it through for generalized foos. And this is exactly the problem that ChatGPT can't do, right? If you ask ChatGPT, if you trained ChatGPT on the foo paper, which exists on the internet, and then you say, prove this theorem for generalized foos, I know exactly what it'll do. It'll write the foo proof, but it will cross out foo and replace it with generalized foo. That's exactly what it did with primes that end in 7. You see, it will just confidently change the word foo to generalized foo all the way through and say it's done. And so that's not right. This is beyond the understanding of the large language model, okay? That was the problem. It's naively pattern matching without understanding. So what does the PhD student do? This is what they might do. What do the first year PhD student might do? They might ask another PhD student, right? They're like, because the guy in the year above them, they know all about generalized foos. So they ask some more experienced PhD student, or they ask one of my postdocs, right? And if the postdoc doesn't know, it's like, oh yeah, I don't know much about generalized foo theory. You should just ask Kevin, because he's the department expert in generalized foos. So then they ask me, or maybe they don't know. Maybe it's 3 o'clock in the morning, right? And they're finally doing some work. It's 3. So they might ask Google, right? That's not an unreasonable thing to do. But unfortunately, generalized foos are a technical research area, so Google might not know it. So they might ask Math Overflow, this is like one of these Stack Exchange sites where a bunch of math experts are hanging around. So this might work. Or they might actually try to engage their brain. The good ones might actually try and figure out why it's true for foos and try and understand things. If you've got a good one, they might do that. That would be great. And now the question is, can we actually, this is not a particularly, this is the bad thing. They might ask me and I might just know the answer, right? I might not know, I might actually know how to do this problem that I've asked them. Right? I might know the proof of paper, I might know exactly what's going into paper X, and I know exactly how to generalize this. Right? Most of it works, and some bits of it don't work, but for the bits that don't work, I know how to work around that problem. Right? That could be standard. So asking me, they might just get an answer straight away. Right? I might just be sitting there waiting for them to ask. But the question is, can we actually remove, the question is, can we remove me from the picture? Right? Can I be replaced by a computer? So can we do better? The answer might be standard. That's what I'm saying. The answer might be standard. So can we do better? Can we actually give the student some kind of machine that will solve this problem? And as I say, the reason I think this is an interesting question is because if the large language models can't do this, then no way the large language model is going to do my research. Right? I think this is surely some kind of necessary to solve that problem, where the large language model just crosses out foo, replaces it with generalized foo, and says it's finished. Okay, if we actually can get it to start thinking sensibly about what goes into this main theorem of foo, kind of checking that every time you replace foo with a generalized foo, checking that actually this is a valid replacement. So this is why I think it's an interesting benchmark. Can we get them to supervise my PhD students? Can we make a tool for my PhD students so they're not emailing me at 3 o'clock in the morning? And I think that large language models by itself can't do it. But I think that maybe if you put them together with interactive theorem provers, maybe we could make such a system. So I just want to spend the last 5 minutes, I've got 5 slides left and 5 minutes left, so I think we're doing great. Maybe putting these things together, these two things I've been showing you, large language models and interactive theorem provers, maybe we can get somewhere. So what do we need? We need the thing that the large language model doesn't have. We need an accurate big database of correct theorems and also counterexamples, right? We want to make sure there'll be some statement, this is true for foos. This is well known to be not true for generalized foos because everybody knows the famous example of this generalized foo that isn't a foo. And this fact is not true. This big theorem was that, this generalized foo doesn't satisfy all of this stuff. This was the first example of a generalized foo that was provably not a foo because it didn't satisfy something. So we want a big list of theorems and a big list of counterexamples. So that's the back end and formally verified. That would be good. You could write that in human language, but the problem is the computers are not good at reading human mathematics. And then we want some kind of tool that is capable of reading this big database and sort of interpreting. The question is, does all generalized foos, are they all even? Are they all prime? Are they all whatever? Do they all have property 23? So we want some kind of tools that already exist. That will actually process the question that the student's asking and try and put together either a proof or a counterexample from the big database. And then we want some kind of human-friendly front end so that the poor humans don't have to learn that lean twaddle I was showing you earlier, right? Because that auto-generated stuff is not really. You have to learn a programming language to understand that. So that's the idea. And can we do that? Like the counterexample finders and the hammers, that's there already. Those techniques have already been. And human-friendly front end, that can be built, right? ChatGPT is exactly a human-friendly front end to some kind of computational system. So humans are already very good at that kind of thing. And so now all we need is the gigantic database of modern results covering all of pure mathematics in a form understandable by an interactive theorem prover. And that's currently the roadblock. And the reason it's a roadblock is because I just want to take the internet and feed it to some large language model and get it to translate the entire internet, all the accurate bits of the internet, into lean code. And that's difficult because computers aren't very good at reading the human literature. And one of the reasons for that is the human literature's got mistakes in, right? So you can't possibly, if there's actually some argument which is incomplete or incorrect, then how can you possibly expect any kind of machine to translate that into accurate code and interactive theorem proof, because it can't be done. Right? The human literature is full of mistakes. Sometimes very small. A lot of mistakes that don't matter, but they're still there. And right now, humans are not rewarded. So we want, humans could do it, but then you've got to persuade the humans to do it, right? But humans aren't being rewarded. The system doesn't reward humans for doing this because it's not proper research in maths. And it's like the computer scientists are like, why do you even care about this weird math stuff anyway? So it's sort of falling in between maths and computer science. So what I've noticed that the thing to do is you say, why don't we do something big? Why don't we do perfectoid spaces? Or why don't we do the liquid tensor expression? Why don't we do Fermat's last theorem? You propose a big challenge and you get a whole bunch of young people interested. And the young people come along, you tell them to do some fashionable mathematics, and they come along and what you don't realize is they're secretly writing your library for you. You don't even really care about the one thing. You've chosen a random theorem. You don't really care about the theorem. You will care about growing the library, really. But this is the trick. You find a challenge that you can sell, the community come along and like, yeah, let's try and prove this challenge. And you're secretly making the library. And so the databases are getting bigger because people like me are going around and saying, oh, why don't we do this problem next? Why don't we do this problem? And getting people on board. But unfortunately, we've still got a huge amount to do. So here's an example of a mathematical database. It's called the Stacks Project, and it's 7,000 pages of PDF. It's just thousands and thousands of theorems in algebraic geometry. And if we could get the large language model to translate that into lean, that would be great. But the large language model can't do it, okay? It struggles to read the proofs, and probably some of the proofs are wrong. I translated some of these proofs into lean by hand, manually, and some of them I did find mistakes. It's like, wait a minute. Like the computer says, I don't get this, and you're just like, actually, yeah, that is slightly wrong. What's up there is slightly wrong. But one thing, this is the last thing I want to say, one thing they're getting very good at is translating the statements. Right? The proofs are kind of hard, but just translating the statements. So here's an example. This is from my blog. This is the idea. This is a machine, right? The human says, if G and H are groups and F is a homomorphism from G to H, then for every A and B and G, F of AB is F of A times F of B. You type that in, and the computer attempts to translate that into lean. And it works. And so there's Zangir Azabayev. He's an undergraduate at Yale. He made that system. And Gadgil is also, where is somewhere else in the world where this sort of thing is happening? Translating mathematics into lean. Here, Siddhartha is doing that stuff. So here's a summary of the talk then. Mathematicians should be aware that new tools are coming. I don't think the large language models are going to do it by themselves. But if you can persuade people to write code in an interactive theorem prover, writing code in interactive theorem provers, that should say, which corresponds to statements of proofs and hard theorems, is fun. And it also might be important. And if you're a mathematician or interested, talk to Gadgil, right? Find a mathematical statement or proof you want to formalize, and then ask him how it's done. So I've got no time left, so I won't tell you about that thing there, but there's an advert, and thank you very much for coming.
It looks like the putting together of this chatting entity as well as Lean, which can check, is mimicking the way we probably discover a proof.
Yeah.
So can you speak a little bit about the similarities or the differences or both?
Yeah, this is why we need to put, this is I mean, people don't know, yeah? That's what we want to do. Yeah, I think this is exactly right. We have this problem. There's infinitely many things you can do next. And that's why it's not going to be as easy as chess. But humans have got ideas, and if ChatGPT can say, yeah, maybe the next idea is this. But the problem is, right now, they've tried it, and right now, we're at undergraduate level, right? Beginning undergraduate level. But yeah, will it get better? I think it might do, mightn't it? Tim Gowers has got some billionaire back. He's a Fields medalist in Cambridge. He's got some billionaire backing him. And Anand, who I mentioned, Anand, he's going to work with Gowers come this October. I do think that there is some potential here, but...
Just to follow up, the solution to the 1964 Olympiad question, was this discovered in this way where you tell ChatGPT that this proof that you've given is not correct, and then ChatGPT tries
that's what was happening. I mean, it wasn't ChatGPT, but it was Facebook's large language model. Okay. But they were like, here, what about this? And then the theorem prover's like, nope. Yeah, they were like, okay, well, what about this modification? It's like, nope. Yeah, and eventually it said yes.
Another traditional way in which computer was used to make calculations and make, come up with good conjectures like BSD.
Oh,
Can this do it? I mean...
No, absolutely not. That's not true.
Is that harder? Or,
the DeepMind worked with these... Do you know this work with Lackenby?
No.
Lackenby, they used a language model. They had a big database in knot theory. And knot theory invariants, there's continuous ones and discrete ones. And they thought an interesting conjecture would be how to relate continuous and discrete knot invariants. So they fed it they just fed a neural network, these databases, and said, can you predict one of the discrete invariants from the continuous invariants? And the computer was like, oh, actually, I can, one of these things. And they were just like, oh, that's interesting. And then they looked at the numbers, were like, which continuous invariants are you using to predict this discrete invariant? And the neural network was like, well, this one, and this one, and this one. And then the human knot theorists took over, and they put some conjecture together, and then they proved it. And so this conjecture came from the computer. The idea that the conjecture was there came from the computer, and the humans conjectured, and the humans proved it. And it was also in Nature. So it's 2 examples in the last 2 years of pure maths in Nature. And the other one was this. So that was kind of an amazing thing. Yeah, I could have gone on about that in my talk, but yeah.
So my question is, I believe the problems that we have in this large language model is exactly just using neural networks and solving backpropagation algorithms and just trying to fit the data that you have. Mm-hmm. And essentially the increase in the chess game that was referred was because we ended up using reinforcement learning algorithms where we learned action spaces and what actions or what values we are actually, each action has. So do you think, and that would help it learn paths that it...
we have infinite action space. Yeah, this is a big problem.
Yeah, but you can basically use neural networks to approximate the action space in some way, and finally use reinforcement learning to for models to learn paths or even discover paths which are not discovered.
Yeah. That's what people are doing. But unfortunately, we're only at undergraduate level. But it might get better. but we just don't know. Yeah, but what you're saying is that we need both ingredients at once. And I agree with you. And people are thinking, but this is state-of-the-art stuff.